In this video you will learn about the concept of energy conversion efficiency related to electrical devices such as electric motors, for example. We'll take a brief look at some of the most important terms such as energy and work and power, and I'll also show you in an example in which we will determine the efficiency of an electric motor which shall lift a certain load off from the ground. And as always, there's a summary at the end of the video with the most important facts conveniently presented to you on a single slide. So stay tuned until the end. My name is Andreas from The Fearless Engineer, and here we go. Now, before we start, let's look at a broad definition of this concept of energy conversion efficiency. Let's say, for example, taken from Wikipedia. It says there that energy conversion efficiency is the ratio between the useful output of an energy conversion machine and the input. So an energy conversion machine, this can be, let's say, an electric motor. This can also be a battery. This can be a power plant. It also can be, let's say, a resistor or any other device which you might find in electrical circuits. Also, outside of electrical engineering, this concept of energy conversion efficiency is broadly used all over the place. But in this video here, we're going to focus on the definition or on the meaning behind this concept here, specifically applied to electrical engineering and electronics. So it's about a ratio between a useful amount of energy and a total amount of energy we put into to power a machine. And this definition of useful, of course, varies. But let's say you wanted to use a light bulb and you power the light bulb using electricity from your wall socket, and then you find that the amount of light which the light bulb produces pales in comparison to the exorbitant amount of heat the light bulb produces. You do not want the heat. This is not useful to you. What you want is the light, and then you would take the light or the energy spent on light as this useful output in the energy conversion concept and relate it to the total amount of energy you need to power this light bulb. So what's it all about here on this in this video? When we design technical applications, it is very important to consider. I used the example of light bulb, but you can apply it to all other components of a circuit as well, to consider how efficiently these components handle the energy which is provided to them. And secondly, with efficiency or energy conversion efficiency, it's possible to evaluate the efficiency of both consumers and producers. In this list of devices which you can use to assess the efficiency, I listed both the consumers, which are, let's say, the resistor, the light bulb, or a transistor, or let's say the processor of your smartphone. But you also have the producers, which are the battery, the power plant, the windmill, and all the other possibilities of how energy can be produced to power your devices. And this conversion efficiency is about both. Now, before we dive into this concept of conversion efficiency, let's quickly recap some items which we need in order to transfer this concept to the world of electrical engineering. The first is that voltage sources generate an electric field and transfer potential energy to the free electrons in a circuit. We have talked about what free electrons are. If you're not sure what this means, you might want to recap this, watch this video. And when we talk about valence electrons and how they move driven by an electric field through a conductor. And secondly, work is performed on the electrons, the free electrons in a circuit, which converts their potential energy first into kinetic energy and then into other forms. We have previously talked about work and energy, and we have seen or looked at this analogy of the apple hanging on a tree, which gives it potential energy, and when it falls, this potential energy of the apple is converted into kinetic energy. And when it impacts, obviously there are other forms of energy at play, but this conversion of one energy form into another is what we call work. And thirdly, in addition to the desired forms of energy or power which we want, some of the energy is converted into undesired forms, which might be the heat of the light bulb example I have been making on the previous slide, or the heat produced by a motor when it's powered. And there are many other examples of undesired forms of energy, of unuseful forms of energy. And lastly, before we start, to describe the quality of a technical device, we need a measure for the proportion of the original energy invested that could be converted into this desired form. And the aim now is to simply make an example and run a few numbers to see what's, for example, the energy conversion efficiency of an electric motor, which is used to lift a load to a certain height above ground. So now let's make this example. In order to determine how efficiently, let's say, an electric motor works, here you can see a motor which needs to lift a load up from the ground. This load weighs half a ton, and the aim of the motor is to lift it up from ground position to a height of 10 meters above ground. And this is all happening within the gravitational field of the Earth, which is at 9.81 meters per square second. And we want to determine the efficiency, the energy efficiency of this electric motors. And in the first step, we want to determine the amount of work being performed. So in order to find out how much energy we need in order to perform this task, we first need to know the change in potential energy which the weight experiences when we lift it to a height of 10 meters. And this can be easily done by using this simple formula here. The work needed to be performed on this weight is the product of mass of the weight times the gravitational pull of the Earth times the height to which we want to lift it up to, which is 10 meters. And if we insert all the values, 10 meters, half a ton, 9.81 meters per square second, we arrive at 49,050 joule of work being which is needed to lift up this weight to the height of 10 meters. This is the useful amount of energy we need to invest in order to perform this work. Now that we know the energy needed to lift up this weight to the height of 10 meters, we now need to take a look at the time it took the motor to do this. Because when we talk about energy conversion efficiency, we can do two things. We can either use the energies only, or we can also look at the power needed to perform a certain amount of work. Both are very similar and they are related over the time t. And with electrical applications, as we will soon see, it is often useful to use power instead of energy, because we can use the power law to use, let's say, voltage measurement and a current measurement to arrive at the electrical power needed by a certain device, let's say this electrical motor here. And if we divide the amount of work being performed by a time t, which it took to perform this work, we can convert work or energy into power, which is what has been done here. After timing the amount of time it took to lift the weight, which is 30 seconds in this example here, we can now compute this ratio of the work being performed, 49,050 joule divided by 30 seconds. And then we can say the motor, the power needed to lift up this weight was at 1,635 watts. This is the useful power needed to lift the load. And now we can look at the electric power which was used by this motor here to lift the load. The motor basically can be seen as a resistor in a circuit. You can see it here in the little schematic where you can see the power source on the left and the motor here on the right. And if we say that the wall socket, let's say we're in the USA, the wall socket provides us with 115 volts, and the current which is drawn by the motor is at 15 amps. We can simply apply the power law, compute the product between voltage drop and current flow, and then we arrive at a power of 1,725 watts. This is the electric power used by the motor during the lifting task. And now we have both the power needed to lift the weight, which we have computed on the previous slide, and we have the power used by the motor to be powered over a period of 30 seconds to lift this load. And by taking current and voltage measurements and this value here, we can now on the next slide compare the electric power and the power to lift the load to arrive at this definition of efficiency, which we can apply to this example here. And on this slide, we are computing the actual efficiency of the motor by looking at the ratio of the useful power P used divided by the operating power, or the power used to operate the motor. The power which is applied to the useful task of lifting the weight is at 1,635 watts, and the power used to operate the motor using the power law is at 1,725 watts. And by computing this ratio, we arrive at a value of 0.95, which roughly this value here, which gives us the information that the energy conversion efficiency of this particular motor here is at 95%. This is the energy conversion efficiency, or short efficiency, of this particular motor here. And the question is, in case you are wondering, what has happened to the missing 5%? Where has this this energy disappeared to? Energy cannot be lost, it cannot be destroyed, it can only be converted, and the information that we have lost somehow 5% in the process of powering the motor to use to lift the load. The question is, where has this gone? If you have any ideas, don't hesitate to drop me your suggestion as a comment in the comment section below, and I will get back to you and comment on your opinion on where this missing 5% have gone. Now let's quickly summarize the main concepts you have learned in this video. We have established energy conversion efficiency as a measure for assessing the effectiveness of energy conversion achieved by a certain technical device. Secondly, we have seen that efficiency is calculated as the ratio of energy spent to energy invested, and especially with electrical application, it makes often sense to calculate this efficiency from power instead of energy, which is because we can easily use the power law to, let's say, use voltage and current measurements to compute the power consumption of an electrical device, which is often easier than using the energy. And thirdly, lastly, the law of conservation of energy states that the efficiency can never be greater than 100%. There are no perpetual motion machines, and even achieving 100% in practice is not possible. We will always be below 100%. And just to give you an idea of certain effectiveness examples from practice, the light bulb we have already talked about is at only 5%, which is the major reason it has been banned in Europe. And we are now using mostly energy-saving lamps and LED lamps, but light bulbs are no longer sold here. Secondly, we have the electric motor, which is usually above 90%. In our example, it was at 95% even. This is a typical value, and this shows the potential of electric motors when we compare them to, let's say, combustion motors, which are only roughly somewhere at around 40% of energy efficiency. And the last example, which is the solar cell, is at only 12%, but since it does rely on the sun and not on fossil sources such as oil or coal, this is still a very useful addition and a very interesting power source to use in practice. Now this was all for this video here. If you have any questions, don't hesitate to drop me a comment down below in the comment section. Also, if you have suggestions for future videos, leave me a comment here. And if you liked the video, consider leaving a thumbs up, consider subscribing to my channel. And as always, I wish you a nice day. See you next time here on The Fearless Engineer. Let's quickly summarize the major findings from this video here. We have seen that energy efficiency is an established measure for assessing the effectiveness of energy conversion achieved by a certain technical device. We have also seen that efficiency is calculated as the ratio of energy spent to energy invested, and if we don't have the energy available, we can also use the power, which is something which is often used with electrical devices, simply because the power law gives us the power as the product of current and voltage, which can easily be measured by using, let's say, 2 multimeters. And thirdly, we have seen that the law of conservation of energy states that the efficiency can never be greater than 100%. There's no perpetual motion machine, and even achieving 100% is not possible in practice. On the bottom here you can see 3 devices to conclude this video. The effectiveness or the efficiency of a light bulb, which is only at 5%, and you can also see the reason why these have been banned across Europe because of this really low efficiency, because 95% are converted into heat and only 5% are converted into light, which is what we want from a light bulb. Then you can see electric motors, which are above 90% in most cases, and also a solar cell, which is at only 12%, but since the energy is coming directly from the sun, we can live with a very low energy efficiency factor here. So this is all for now. If you have any questions, don't hesitate to drop me a comment down below in the comment section. Also, suggestions for future videos should go there. I wish you a nice day. See you next time here on The Fearless Engineer.